Good afternoon, and I welcome you all to this session of fluid mechanics. Now, last class, if we recall, we are discussing the flow through a pipe bends, and the flow through a pipe bends exerts the force on the bend, and we have seen that by the analysis of finite control volumes, with the application of the analysis of finite control volumes, how we can find out these forces exerted by the flow of fluid through the bends on the bends. Now, today we will be discussing a similar type of problem with the analysis of finite control volumes when the flow impinges on a surface. It may be plane surface, it may be curved surface. When a flow of liquid impinges on a surface and then flows along the surface, then what is the force exerted because of this impingement of the liquid jet on a surface, and accordingly due to that force, if the surface moves with some velocity, what is the power generated, which is very important and forms the background of the turbo machines, principles of turbo machines. So, therefore, today we will be discussing the force exerted due to the impingement of a liquid jet on a surface, solid surface. First, we will restrict to plane surface. Let us see the problem, analyze the problem. Let us consider a surface like this, which is plane, in a sense that this surface is inclined with respect to the liquid jet. Let liquid jet strikes the surface like that, which is being issued from a nozzle, and it strikes the plate, and then the jet, after striking the plate, glides along the plate. Let it glide along the plate. So, this is the inflow, and after impinging I show the liquid sheet that the flow is like this. So, liquid is flowing along the plate, and we consider initially the angle of the plate. In general, the plate is inclined with respect to the axis of the incoming fluid. Let this be the horizontal direction, then plate may be in the vertical plane. So, this will be in the, or even in the horizontal plane, it may be vertical, it may be horizontal, but this inclination angle is theta with the axis of the incoming flow. Now, how to analyze this problem? In a sense, practically what happens when the fluid impinges on this plate and glides along the plate, some force is being exerted on the plate. So, it is obvious, you can conceive very well from practical realization that if the plate is made free, it will be moving in some direction like this, depending upon the net force acting on the plate. So, therefore, to keep the plate stationary against this flow of fluid impinging on it, some force has to be given on the plate. So, therefore, we can find first what is the force exerted on the fluid by the plate due to its flow through the plate, and what we do for that, as usual, control volume. We can take a control volume like this. Well, we can now take a control volume of the fluid like this, a fluid element just like this. We can take a control volume of the fluid element like this surface of the fluid element just adhering to the plate surface, and one of the faces perpendicular to the inlet flow, and this faces perpendicular to the outlet flow. Now, one thing we will have to first understand from the physical situation, that if v is the inlet flow velocity, so the outlet flow velocities also will be v, provided certain conditions are maintained. What are those conditions? If we consider the jet is, or fluid flow, stream of fluid impinging on the plate, throughout the pressure is atmospheric, there is no pressure change and all these things. That means in atmosphere this fluid jet is exposed and the plate is kept at atmospheric condition and the fluid strikes. That means throughout the pressure is same and is the atmospheric pressure. And moreover, if we consider the fluid to be inviscid, that means the friction between the fluid layers and also between the fluid and the solid surface to be 0. That means considering the frictionless fluid, that means frictional interaction with the fluid or the liquid and the surface to be 0, and pressure throughout the atmospheric pressure, we can write the velocity of exit will be v. This is because if we write the Bernoulli's equation at a point here and there at the exit, then we can see since the pressure remains same, velocity remains same. But another assumption should be there, that if the plate is in the vertical plane, then the elevation difference from this point to this point or this point, the elevation difference from these three planes, one is the inlet plane, two are the exit planes, are 0. For a surface at horizontal plane like this, then a question does not arise, but for a vertical plane, the surface is at a vertical plane, then the elevation difference should be negligible. So, in that case we can consider, we can write that the velocity at inlet and outlet are same from the Bernoulli's equation. So, therefore, outlet velocities are v. Well, now if we draw the here, now draw the the control volume. Now, if we draw the control volume like this, this is the control volume of the fluid, control volume. Now, we can analyze the situation. Now, this is the inflow velocity v, this is the outflow velocity v, this is the outflow velocity v. The sheet thickness or cross section will definitely change, because now this angle, let us consider theta, because if we consider the volume flow rate as q, where q is equal to v into, if we consider a, small a is the cross sectional area of this jet, then v into a. Now, this q will not be definitely distributed in the equal manner or equally distributed in both the directions. It cannot be. In general, this will be different, and we will find it analytically that this will be different. Let q1 and q2 are the volume flow rate through these two paths, which is being divided after impinging on the plate. Now, first of all, we will find out a relationship between q1, q2 and q through the application of the momentum theorem to the control volume, and also we will find out by this application of the same theorem to this control volume the force acting. Now, our next step is to choose the reference axis. Now, here one trick is there, the reference axis is not chosen parallel to the incoming jet velocity and perpendicular to that. Rather, it is chosen as parallel to the plate, that means this direction, and perpendicular to that. So, this axis is n, for example, and this I write as s, that means let O origin at any point here. So, OS, ON are the reference axis which is parallel, and let this direction is the positive for this S axis and ON is perpendicular. This trick is because of the fact, with the assumption of the inviscid flow, there is no frictional interaction, and there is no frictional interaction between the plate and the liquid. So, the net force acting along the direction of this plate on the fluid element will be 0, because net force acting in this direction when the flow is in this direction, because the outlet flow, the fluid stream will be flowing along the plate. So, therefore, if any force along the plate acting on this control volume at this surface will only indicate the frictional effect, because normal force between the two contact surface, as you know, always acts perpendicular to the surface. So, any force acting parallel to the meeting contact surface means the frictional effect. So, if you neglect the frictional effect, the force acting on the fluid, there should not be any component of force acting on the body of fluid in the direction of S. That is the main assumption and main concept. So, we can tell the Fs, the net force in the x direction, has to be 0. This is not from the concept of momentum theorem from the control volume, it is simply from the physics of the problem that we take an inviscid fluid, and because of this we take the axis or choose the axis OS and ON, that means one axis parallel to the plate, that means parallel to the flow direction at the outlet planes, and one is normal to that. So, this is the key point. Now, we simply write the momentum theorem for this control volume in S direction. What is that momentum theorem? That means the net rate of momentum efflux in the S direction from the control volume is equal to the force in the S direction to the control volume, which is 0. So, I can get a constraining equation. Now, let me see what is the net rate of momentum efflux. If Q2 is the volume flux, so rho Q2 into V is the momentum efflux in this direction. What is the momentum efflux due to this? This will be plus, so momentum is coming out from the control volume in both the planes, rho Q1, please tell, into minus V, because this V is in the opposite direction to the coordinate axis OS, taken positive in this direction. Well, so this minus the incoming velocity of the fluid along this direction, that means incoming momentum, that means this direction. So we have chosen this direction as theta because this angle is theta. So therefore this will be v cos theta. Well, and this v cos theta is in the positive direction of the axis, so it is plus v cos theta, but minus sign is because of the fact minus the influx, efflux minus the influx. So rho q v cos theta is equal to 0, is equal to, rather I can write Fs, which is by definition from the physics of the problem is 0. So if you write this, rho cancels out, which is not 0. So what we get? We get q2 minus q1 is q cos theta. Okay. Another relationship between q2, q1 and q we can find from which equation? Please tell me. q2 plus q1 continuity is equal to q. Simple continuity, conservation of volume flow or mass flow. Rho constant means the conservation of mass flow and volume flow are same. That means the volume flow rate which is coming is getting divided into two parts. So q2 plus q1 is q, which finally gives us, if you solve this, then what we get? q2 is equal to q by 2 1 plus cos theta, and q1 is equal to q by 2 1 minus cos theta. So these are the two important relationships. That means q1 and q2 are divided like that. Depending upon this theta value, if this theta is acute and the plate is inclined in the position as shown in the figure, the amount q2 will be more than the q1. So q2 is this, q1 is this. Now to find out the force, now you see from the basic physics, we have already defined the Fs is 0. So therefore if we choose two axes like that OS, ON, we can tell the net force acting on this control volume is only in this direction, and that is equal to Fn, and this Fn we can find out from the application of the momentum theorem with respect to the control volume along ON axis. Let us write it. That means the net momentum efflux from the control volume, that means along ON. Well, so what is that? Please tell me. Rho q2, now velocity v. So therefore we have to find out it is 0, it is 0, that means 0 plus rho q1 0, that means no efflux minus the influx. What is influx? Influx is, so this component, and that is in the positive direction, that means rho q v sin theta. It is very simple, and that is equal to the force acting, let Fn. Fs is 0, Fs which is 0 is equal to Fn. So therefore we see that Fn becomes equal to minus rho q v sin theta. So under these conditions, positive value of sin theta, so this is minus, that means the forces acting on the control volume is in the opposite direction, that means this is the Fn. So therefore the force acting on the plate is in this direction, perpendicular to the plate, in this direction, Fn. Magnitude is rho q v sin theta. This negative sign indicates the value opposite to this direction is positive. So therefore the forces acting on the plate, that means let us write this Fp, the forces acting on the plate is equal to plus ho jayega rho q v sin theta. That means this is acting in this direction with a magnitude of rho q v sin theta. Well, now in this case, if we consider the plate is allowed to move, or we maintain a motion of the plate in this direction with magnitude u. That means if the velocity of the plate in this direction is u, is a practical problem. If we maintain the plate under this force to move only with this velocity in this direction, then we can find out the work done. Now this q is the volume flow rate. We consider this q is the volume flow rate, so rho q is the mass flow rate, so it is the rate basis. That means work done per unit time. That means we can write is dw dt, d with a cut you can write, or del w del t, sorry, because it is not a perfect differential, or power developed because of this impinging fluid jet. If this plate is moving with u, is very simple, it is the force component in that direction into u. That means it will be Fp, Here better we understand better, it is Fn, it is Fp rather you write. Now we have given the Fp, that means rho q v sin theta. So again we take a component in this direction, that means again sin theta will come, that means Fp sin theta into u, because we know into u. So the work done is the force into displacement in the same direction. So it is power because it is per unit time. So therefore we can write rho q v into u sin square theta. So this is the, therefore now u I take a absolute value, because sometimes the plate can move in this direction, in that case the work will be done against this force, and plate may be moving in this direction, work will be done by the force applied by the liquid to the plate, but in both the cases the power consumed will be rho q v mod of u, that is the speed of the plate times sin square theta. All right, okay, clear? It's very simple. If any concept, any problem is there in the concept, you tell me. All right, next part, if there may be a case when the plate may move with a velocity. Now if the plate starts moving with a velocity u, now here I have done the plate moving already, but problem is that when the plate moves I cannot write this. Though now I have written this thing v into u sin square theta, but it is not correct actually, because when the plate moves with a velocity u, for the force, just for your concept I have done this thing, but there is a mistake in this expression. Now I will correct it, because when the plate initially moving in this direction, then when it starts moving, even if it does not move initially, or if it starts moving, so after the motion is set into the plate, then the force acting exerted on the plate is not given by this expression. Why? Let us see that. Now let us consider the plate is moving now with a velocity u. Just for the concept I have written that, but that is not correct in analytical expression. Let is moving with u. Now what happens if the jet comes like this with the velocity v, that is all right, so long the pressure remains same, the velocities will remain same. But now the difference is that since the plate is moving with u, if I consider a fixed frame of reference from an absolute fixed reference plane, that means if I take any coordinate axis at this point, fixed point, say whether this is parallel and perpendicular to the plate or parallel and perpendicular to the incoming direction jet axis, it does not matter, the flow becomes unsteady, because if we consider a point here O stationary with respect to an absolute static frame of reference, so plate will move like that. So plate will not be fixed at that point A, after some time plate will move, so that the flow structure here will not be same. So fluid jet will come here and then this thing will appear somewhere here. So the things here will change. Or we can tell, if we consider a point here where nothing is there, no flow, flow 0, no flow field is there. After some point the flow field will gradually be developed, this jet will come and ultimately some parallel initial velocity v, then again this type of velocity vector will come, which means that with an absolute frame of reference the flow is unsteady. But if we observe the flow, just I gave an example earlier, that if we observe the flow in a river while sitting on a moving boat or a moving steamer, the flow surrounding the boat or steamer will appear steady. Similarly, if a person observes the flow field who is moving with this plate, he will see always a steady flow field like that in the immediate vicinity of the plate, which mathematically means that I will take a control volume and also the axis attached to the control volume which is moving with the plate. That means here comes the concept of moving control volume. That means I will consider a fixed region like this of fluid as I take as the control volume. Well, the concept is same. So this control volume, we will take the same control volume, but the control volume is moving also with the speed u, and we will fix the coordinate axis as s and n with the control volume, and control volume is moving. That means now I can tell the problem like that, this is my control volume, so that this is my control volume. Well, this is my control volume, but this control volume is also moving with the same speed u. So therefore, to make the problem steady, we attach the coordinate axis to the control volume, that is moving coordinate axis. Sometimes in the language of mechanics we can tell the coordinate axis is moving. So, you can define in that way also, with a moving frame of reference the flow situation may remain steady. That means though the actual flow is unsteady from an absolute frame of reference, but with a moving frame of reference the flow will be steady. The situation is such that if I take a moving frame of reference OS ON which is displaced with the same velocity u, that means with respect to this axis the flow will be steady. That means in other words, through my control volume statement or control picture of control volume, I can tell that this control volume is taken which is also moving with it. That means I consider a control volume fixed region, when the plate moves the control volume is also moving. Now, if we attach the coordinate axis with the control volume axis are moving, that means any analysis with respect to this axis will be done provided the parameters regarding this velocity has to be made relative to the axis, because the analysis will be made with respect to the axis. So, therefore, this will be with respect to the control volume. That means we make now control volume fixed, or other way we can tell we give a opposite direction velocity to fix the plate. That means it will be similar to the earlier case of a absolutely static plate with changed values of this. In that case, this will be V minus u and the fluid will leave also with the velocity V minus u. Fluid will also leave with the velocity V minus u. That means the entire problem is now scaled to a static plate problem or a static control volume problem, where instead actual velocity is V, instead of V the fluid is coming with V minus u, V minus u, V minus u and leaving with V. So, in that case we can write the Fs is as usual 0, because even if there is a motion, so relative velocity will be 0, and because the fluid is frictionless there is no force acting in the S direction. Alright, any problem? Please ask. So, now Fn is equal to, in the similar analysis we got rho q V sin theta, if you see the earlier one. So, only thing is that instead of V I declare V is equal to V minus u. Just means a simple one statement that I declare variable V as V minus u. So, therefore, it will be rho q V minus u sin theta. Alright. Now, here q expression, if we see the earlier one, q expression was V into A. That means what is the flow rate that is issued by a nozzle, for example a static nozzle, that is V into A, because this is the area of the jet issued and that is the velocity V which is maintained constant. The same flow was received by the plate, because there is no discrepancy, so q is V into A. But here you tell me, even if the nozzle issues the velocity V, so with the how much jet water or how much flow rate is received by the moving plate u, it will be rho into, if A is the area of the cross section of the jet, A into this is moving with u, it will be V minus. And obviously, when this velocity of the plate will be equal to V or more than V, the liquid will not be able to impinge on it. Limiting case is V is u is equal to V. If the plate moves at a rate faster than the incoming jet velocity, so jet will never strike the plate. So that you know from the common sense that q, the flow received by the plate, is rho A V minus u. So, in terms of that, it is a very important concept, we can write rho A V minus u whole square sin theta. And this case only the power developed, the question of power developed comes, and in that case P will be, which we did here for an understanding, that V u sin square theta. So, simply this V will be replaced by V minus u, and q also V minus u will come. So, in this case we could have written this thing, a pseudo expression rho q. So, q is A into V, so A into V square u sin square theta. So, in this case it will be, instead of V square, V has been declared as V minus u, it will be V minus u whole square. So, therefore, we can write rho A. So, automatically here also V minus u square sin square theta, u into, u is as usual sin square theta, because this into u sin theta. So, this is Fn into sin theta, that means the component of this is theta, sorry, I am sorry, this is theta. So, this component will be sin theta. So, theta is defined like this is theta. So, this is the expression for the power. All right. Similarly, when the plate will be moving in the opposite direction, this will be substituted by V plus U. In that case, the flow rate received is more than that issued by the nozzle. So, these are the two typical cases. Now, in this case, if you are interested, I can show you another one thing, that now this V minus U is actually the relative velocity of the liquid coming out from the plate. That means this velocity in this case is V minus U. And actually for a shockless flow, the relative velocity should be parallel to the solid surface, which means that this liquid should glide along the solid. That means with respect to solid, always liquid should glide along the solid. That means the relative velocity vector will be all. That means a person moving or sitting at the plate will see always the liquid going out at the final plane, discharge plane, which is gliding along, that is parallel to the surface, and this is the relative velocity. We can find out what is the actual velocity. By doing so, what we can do, we can make the relative velocity is equal to vector is absolute velocity minus the velocity of the plate. So, therefore, if we make this, we will have a velocity triangle. That means, if this is u, so this will be your V0. So, V0 is the absolute velocity. That means, this is V minus u relative velocity and this is u. This gives the vector notation that V0 minus u is Vr, or Vr plus u is V0, V. That means, Vr plus u is V0. Here I write V0. Similarly, here also, if this be the V minus u, whose direction will be always along the plate, you will have to remember throughout afterwards in your turbo machines course also, that the relative velocity of the fluid when the fluid flows along a moving surface, then the relative velocity of the fluid coming out from the surface is parallel to the direction of the surface, because the fluid should glide along the surface with respect to the surface. Therefore, this is the V minus u direction, and I can make a V0 here, and this is u. So, at the outlet, the velocity triangle, these are known as velocity triangle, that is a vector diagram. So, V minus u, so this is the relative velocity, so this is the plate velocity V0. That means, V minus u is V0 minus u, or V minus u plus u, that is relative velocity plus the plate velocity with respect to which the relative velocity is defined, is the absolute. That means, therefore, the fluid is coming with an absolute velocity vector whose direction is this, magnitude is this. Its direction is this, magnitude is this, where these are the relative velocity. All right. Okay. Now, we come next to the curved surface, flow through curved surfaces. Now, which is very important and forms the background of turbo machines. This will be again told in your fluid machines class. Curved surface, I repeat it again. Now, let us have a problem like this. There is a curved surface like that. Let us have a curved surface like that. A curved surface like that. And let this curved surface is moving in this direction with a velocity u. Well, so the fluid enters at this point on the curved surface and glides over this curved surface and coming out. Since the fluid is the curved surface is moving with this velocity u, so the fluid here will have a relative velocity, that is, we can have a velocity with relative to this curved surface. Let us draw the velocity triangle. Well, this diagram is little, this is Vr, let this 1, this is u, and let this is V1. This is the absolute velocity and this is the relative velocity. Similarly, we have this relative and the absolute velocity. Well, Vu plus Vr is therefore this is V2, VR and this is U. That means we can tell that if a fluid strikes the plane here at 1, section 1 with a velocity V1 and comes out with a velocity V2. These are the absolute velocity. I have drawn the velocity triangle beforehand. So, let us first think the problem in this way. A liquid jet impinges this curved surface here with a velocity V1 and which makes an angle, like this angle is alpha 1 with the direction of the motion of the curved surface, and comes out with a velocity V2 which makes an angle alpha 2, okay, with the direction of the motion of the plate U. All right, and let us analyze the problem. What we will do? We will take a control volume like this, control volume of fluid touching the plane, some infinite small fluid element as the control volume. Understand? So, I am not again doing it separately. Now, this control volume will be moving with you and we fix an axis with the control volume in this direction, one in this direction which I call x, another leg in this direction y. So, therefore, we attach the axis with the control volume, and control volume we are taking a moving control volume, moving with uniform speed, because here the system is moving with uniform speed. So, therefore, the axis is moving with uniform speed. So, therefore, the axis is moving because attached to control volume, and the analysis will be made similar to the earlier problem with respect to the moving axis or moving control volume. So, therefore, this will be made like that, as if the fluid is approaching the control volume with respect to the control volume or with respect to this frame of reference with a velocity VR1, not with V1. Why? Because this is the relative velocity with respect to the control volume. That means this is a relative velocity of V1 with respect to U. That means we will have to vectorially subtract U from V1, and that is done to this by shown by this velocity triangle, vectorial subtraction. Similarly, we will consider the fluid is not coming out with velocity V2, rather it is coming out with velocity VR2. Sorry, I am writing here capital R, better smaller, VR2. So, therefore, it becomes a problem of a static curved surface. A static curved surface is absolutely static surface where the fluid is now entering with VR1 velocity and going out VR2 velocity. For a static surface, the absolute velocity of the liquid is the relative velocities of the liquid, there is no difference. So, now we will solve the problem. Now, if we analyze this with the momentum theorem, now you see momentum theorem we can apply for both x and y direction, but usually we are interested to find out the force acting on this curved surface because of the flow of the liquid. So, therefore, we are not much interested in finding out the force on y direction. Why? Because the curved surface is moving in this direction. So, we are finding out what is the power generated or work done in this case to cause this motion by the flow of fluid. So, therefore, we are only interested in Fx. Fy will be there, which in practical cases of turbo machines, I will tell you some hints afterwards what happens actually in turbo machines. These are taken as journal loads and supported by the bearings. So, let us only find out Fx. Well, Fx. Now, what is Fx? Fx is equal to the net rate of momentum efflux in that direction. Now, what is the net rate of momentum efflux? First, it is the influx Vr1. Let us define this angle. This angle is beta 1. This is the common nomenclature. That means with the direction of the motion, the relative velocity makes an angle beta 1. And this relative velocity angle and the angle of the curved surface at this tip must coincide. Similarly, the angle of Vr2 with this beta 2 must be equal to the angle of the curved surface at this tip. That means the relative velocities at inlet and outlet should match the angle or direction of the curved surface at inlet and outlet. Okay. So, now Fx will be, you tell me what will be the Fx if I make the flow rate is q, which is same throughout. So, rho q into, it is coming with what velocity? Vr1 cos beta 1. So, this is here, so sorry, this will be here, this is beta 2. So, Vr2 cos beta 2, that is in the opposite direction of the positive x direction. So, that will be minus Vr2 cos, clear, beta 2. Efflux must flow into the efflux velocity. Now, efflux velocity component in this direction, positive x direction is minus Vr2 cos beta 2. This is beta 2, so minus Vr2 cos beta 2 because the component is in the opposite direction. Well, minus the incoming momentum or momentum influx. In this case, the component of the inlet or incoming velocity, that is the relative velocity Vr1, is in the positive direction of the chosen axis. So this will be simply Vr1 cos beta 1, and that minus sign according to the formula efflux minus influx. So this becomes simply minus rho q into, I can write this one first, Vr1 cos beta 1 plus Vr2 cos beta 2. So this is the force that is acting on the control volume. The control volume energy by the bend. So the force, but by the plate. Force, x component force acting on the plate will be just the opposite to that with a negative sign. That means the force acting on the plate will be in this direction of x. That means in this direction the force, x component of force is acting on the plate in this direction, whose magnitude is Vr1 cos beta 1 plus Vr2 cos beta 2. Now this Vr1 cos beta 1 and Vr2 cos beta 2, if I draw the triangle separately here, it will be difficult for you to recognize from there. This is V1 and this is Vr1. Let this is Vr1. So this is beta 1, this angle, and this angle is alpha 1. Well, and similarly the outlet triangle, if I draw it here clearly, V2, okay, and this is Vr2, this is U2, and this is beta at the relative velocities angle, and this is alpha 2. Now Vr1 cos beta and Vr2 cos beta is nothing but, this is Vr1 cos beta, and what is Vr2 cos beta? This is entire thing is the Vr2 cos beta. Vr1 cos beta 1 plus Vr2 cos beta 2. Now if I add plus u and subtract minus u, what happens? Vr1 cos beta 1 plus u is this component. Usually this is known as Vw1. Of course this terminology will be difficult for you to understand. This is known as the tangential component of the absolute velocity. Tangential means this direction is the tangent direction. I will explain it afterwards with respect to a fluid machines application, that it is the component of the initial velocity in the direction of the plate motion. Similarly, if I deduct from Vr2 cos beta the u2 component, this will also, then it will come like this. This is Vw2. That means this will be again the component of the absolute velocity in the direction of plate motion. It is easier to deal with this in case of turbo machine, so that Fpx is denoted as rho q Vw1, where Vw1, Vw2 nomenclature is the component of the absolute velocity in the direction of the plate or surface motion, and component of the absolute velocity at the outlet in the direction. That means components of the absolute velocities, the inlet and outlet, in the direction of the motion of the plate or surface. That is the tangential direction. That is why it is known as tangential component of absolute velocities. So this is Fpx. Now we can find out what is the power. Power is rho q, that is the rate of force, rho q Vw1 plus Vw2 into simply u. So this is the power developed because of the motion of the curved surface in this direction due to the flow of the liquid through the curved surface. This happens actually, okay, all right, this is all right. This is like this. This is simply, I tell you, that if the, first of all, is a simple geometrical consideration. You see this triangle, all right. From this triangle, Vr1 cos beta 1 plus u, I add u with this, subtract u from this. So Vr1 cos beta 1, that is this thing, Vr1 cos beta 1, that means this is this projection. Vr1 is this one, this component, plus u, this is u. What is this? This is u. vector diagram, this is V1, this is VR1. So if you add U, so this will be this length. This is nothing but VW1, that means the component of the absolute velocity in the direction of the motion of the surface or plate. Clear? Similarly, if we now deduct from VR2, what is VR2 cos beta? This one is VR2 cos, that if you take a projection, here also we take the projection, you take the projection, then this will be the VR2 cos beta. Deduct U, we will get this. This is not U2, this is U, U1, U2 are same, this is U. So therefore this becomes this part, VR2 cos beta minus U, this becomes this. So this plus this means this plus U minus U. If I take plus U with this, I get VW1. If I take minus U with this, from the velocity triangle I get VW2, where VW1, VW2 are the tangential component of the absolute velocities at inlet and outlet. Clear? It happens, just I tell, time is mostly up, that in case of a turbo machines, you will see there is a rotor and a number of blades like this is attached like that in the rotor. A number of blades are attached, these are the rotor. That means the fluid comes in between the passages of the blades and comes out. That means fluid comes in and fluid goes out. So what is done there, if we take a section at the mid section, we take a section, we will get this curved surface, the flow of fluid through curved surface. We take any representative section of the blade, see from the top, take a section, we see this is moving in this direction, rotating in this direction, turbo machine. So as the fluid enters in the blade passages, there are a number of blades on it and goes out, this exerts a force and ultimately the turbo machine rotates in this direction. So therefore if we take a section like that and we get this is the curved vein like that, then this direction motion is represented, this is the tangential direction. So at any representative section, usually if this is the center, it is taken as the middle height. This is the basic application of turbo machines through this. Then again I tell you what happens in turbo machine, you can better understand if I tell like that. There is a rotor keyed to a shaft. Rotor is a disc, simple disc to a shaft. The disc rotates, and on the periphery of the disc, number of blades with some heights are arranged, and the fluid flows through this. Fluid enters at some section and flows axially through these blade passages, and the power is developed, and the blade and the rotor moves in this circular way. That means rotates about the axis, that is the shaft. Okay. So this is the practical application, and based on this principle of force exerted by the flow of fluid through curved surface, and thus the power developed if the surface is allowed to move. Thank you.